In this lesson, we will cover the Fluvial Geomorphology section of the geography syllabus. Now, when we look at Fluvial Geomorphology, the most important starting point to understand is the hydrological cycle. When we look at the hydrological cycle, we look at the input of precipitation and how that water moves around our Earth and our atmosphere. Now, precipitation falls in the form of snow, hail, rain, sleet, and it falls as input. This is how we get our water. Now, when it falls on the earth, it becomes surface runoff. It runs off our surfaces, and from there, it can either percolate into the soil, but in which it moves downwards into our soil and becomes part of through flow, which eventually moves into our water table. Or from surface runoff, the water can run off into stream channels, and the water is then taken away by stream in water flow and will eventually flow out into the ocean. Once our water is on our surface, we have transpiration, which takes place through plants, and it is the equivalent of evaporation through plants, and this enters our atmosphere and eventually rises, cools, and condenses, forming clouds, and the cycle starts again where the water falls as input precipitation. Or we can have evaporation of any body of water, such as a river, a dam, ocean, lake. Evaporation occurs where the water is heated, it evaporates, rises, cools, as we can see here, condenses, forms clouds, and precipitation falls in the form of input precipitation. It's important to note that impermeable rock cannot be permeated by water, and the through flow simply enters the water table, which does not sink any further due to impermeable rock. Now, potential evaporation is the amount of evaporation that would occur if there were sufficient water sources. This is not something that is often asked, but I have seen it asked before, and it is quite a cool term to know if you were ever asked to explain what potential evaporation is. So the hydrological cycle, as we've said, is the movement of water over and through Earth's surface, runoff and infiltration. It is the transfer of water from large water masses, evaporation, and the release of water from the atmosphere in the form of input precipitation. So sources of water, we have rainwater contributes to surface runoff, we have rainwater that flows over land and into channels, and rainwater infiltrates into the ground to form groundwater in our water table. Now we look at the processes. So we have the evaporation of water from oceans, dams, etc. As moist air rises, it cools and condenses, as we've learned, to form clouds. Clouds are simply condensed liquid on nuclei, and eventually the water will fall as precipitation. It may evaporate back into the atmosphere, or it may penetrate surfaces and become groundwater, as we've seen in the diagram above. Now, when we look at infiltration and runoff, we look at a number of factors that play a part in determining our infiltration and our runoff. If we look at gradient, if we have a steep gradient, our water is going to flow fast and our infiltration will be lower. If we have a gentle gradient, the water flows more slowly and there's more chance for the water to permeate into the ground, and a gentle gradient will increase our infiltration. In the opposite way, runoff will decrease if the gradient is gentle. This is because your water moves more slowly and you have an increase in infiltration. Therefore, there's less water to run off. And if you have a steep gradient, your runoff will be greater because you have less infiltration and therefore more runoff. Vegetation affects your infiltration. If it is densely vegetated, then you'll have more infiltration. Your vegetation traps the water, leading to slower runoff and therefore more infiltration. And if it's sparsely vegetated, then your water will run off more quickly, leading to less infiltration. The opposite is true. If it's densely vegetated, there's less runoff because your vegetation traps your water. And if it's sparsely vegetated, then you'll have more runoff because there's no vegetation to stop your runoff of water. When we look at soil moisture, if your soil is moist, there's less infiltration as there's less capacity to hold water in the soil. And if it's dry, there's more infiltration because there's more capacity to hold water in the soil. Opposite is true of your runoff. If it's dry, there's less runoff simply because there's more infiltration. And if it's moist, there's more runoff because there's less infiltration. With rainfall, if we have a lot of rainfall, our infiltration will obviously be higher. If we have low rainfall, our infiltration is lower. That is pretty self-explanatory. If we look at our runoff, it is the same. If we have lots of rain, we have increased runoff, and low amount of rain, we have decreased runoff. Type of rainfall, if we have soft and soaking rain, we have more infiltration. If we have a hard thunderstorm or a cyclone, hard rain, then we will have less infiltration as there's higher volumes of water and therefore more runoff. As you can see here, hard rain will give us more runoff. Soft rain will soak into the ground and give less runoff. We look at evaporation rates. High evaporation rates will lead to less infiltration because water is evaporated quickly. Low evaporation rates increase our infiltration because we have more water to be infiltrated. High evaporation rates lead to less runoff simply because there's less water, more of it is evaporated, and a low evaporation rate will lead to high runoff because we have more water to run off the surface. When we look at rock types, permeable rock will have more infiltration as the rock is able to allow water to permeate into it and therefore water infiltrate into the ground. And impermeable rock will have less infiltration because the water is not able to infiltrate into the ground. We look at runoff. Permeable rock will decrease our runoff because we have more infiltration, therefore less water on the surface for runoff. And impermeable rock will increase our runoff because we have more water on our surface and less infiltrated. Next, we look at a drainage basin. We need to know these terms and what they mean and how to label them, how to draw them. First, we look at the mouth. The mouth is simply the end of the river where it flows into the sea, as we can see over here. Then we look at a confluence. Confluence is simply the point where two rivers join to become one, which you can see over here. We have a tributary and a tributary joining at a confluence to become a single river or tributary in this point. Then we have a watershed, which is the high ground around a drainage basin that separates one basin from another. So this would be a watershed. It's often a ridge or a mountain range that simply divides this drainage basin from a drainage basin adjacent to it. Then we move on to a tributary, which is a smaller river that joins the main river at a confluence. Here we have a tributary or a source. This would be a tributary that join at a confluence to become another river or tributary in this point that joins at another confluence. Interfluve is a minor watershed between two tributaries in a drainage basin. As you can see here, this would be an interfluve, maybe a ridge or a mountain where water will flow down this side to join this tributary and water will flow this side to join this tributary. Now, in some cases I have seen where they've asked an out-of-the-box question where they ask you what is a distributary. This is simply where one river flows and becomes two rivers. There's not an example on this drawing, but you can imagine if we had one river that then flowed into a river on the right and then a river on the left, that would be a distributary as we have one river flowing into two. Next, we move on to the types of rivers. So we have 4 types of rivers. The first type of river is a permanent or perennial river. This is a river that flows all year round as it always receives base flow during both the wet and the dry season. So if we look at the wet season water table, we can see in a diagram that it is clearly above the riverbed, and in the dry season it may be lower, but it is still above the riverbed, indicating that the river will receive base flow and flow all year round, both the wet season and the dry season. Examples of perennial rivers are the Tugela, the Vaal and the Crocodile rivers, which lie on the east and the west coast of South Africa. Now, if we look at periodic or non-perennial rivers, these are ones which flow only in the rainy season. During the dry season, the water table is below the riverbed. If we look at the diagram, we can clearly see that the wet season water table is above the riverbed, and therefore it would receive base flow during the wet season and flow, whereas in the dry season, the water table is below the riverbed, and therefore it will receive no base flow and it will not flow during the dry season. Examples of a periodic river are most South African streams. Most rivers in South Africa are non-perennial and only flow during the wet season. Next, we look at an episodic river, which is a river that never enjoys base flow. It only flows after heavy rainfall or a flash flood. We can see that in a diagram, the wet season water table is below the riverbed and the dry season water table is below the riverbed. The river does not receive any base flow in the year, and therefore it only flows when there is enough rain in the area to sustain river flow. Many of the rivers in the dry western parts of South Africa are episodic rivers. Next, we look at an exotic river, which is a river that rises in high rainfall areas and then flow through dry, arid regions. You can see that the wet season water table is below the riverbed, and the dry season water table is also below the riverbed. The river never enjoys base flow. Now, these diagrams, when asked in a test or exam to explain an exotic, an episodic, a periodic, or a perennial river, it is very good to draw these diagrams, as you can clearly see the difference between the four types of rivers. Next, we move on to drainage patterns, and these are often asked to be identified. They'll give you an image of a drainage basin and they'll ask you to identify the drainage pattern, or they may ask you to indicate the certain aspects of each drainage pattern and the characteristics that go along with that pattern. So firstly, we look at a dendritic pattern, which is shown by this drawing over here. The pattern is normally tree-shaped. You can see it looks a lot like a tree. Tributaries join at acute angles, as we can see, and there are distinct interfluves formed. So between our tributaries, there would be interfluves. Now, characteristics of this pattern are underlying rock types are uniformly resistant, and there's little variation in slope or gradient. So where this type of drainage pattern forms, you will have underlying rock that is uniformly resistant and there's little variation in your slope. And we move on to a trellis pattern. There will be prominent ridges which lie parallel to each other, as we can see over here. The main river cuts through these ridges, forming puits, as we can see, and tributaries join the main stream at 90 degrees. These would be your tributaries that join your main stream, which runs here at 90 degrees. Now, a trellis pattern will form in an area of alternating hard and soft rock. So your ridges would be your hard rock, whereas where your tributaries flow, you would have softer rock where the water is able to erode and form a river channel. The layers are often inclined or folded, and the strong main stream cuts into the landscape. As you can see here, the strong main stream has cut through the hard layer of rock or the ridge. Then we move on to a rectangular pattern. A rectangular pattern is angular and develops along exposed joints in rock. The surface water flows along exposed joints, so these would be exposed joints, and there are sharp angles in the pattern of the stream. This type of pattern will develop on a well-jointed rock outcrop where the joints are where the water would be able to flow and erode, and the joints exposed at the surface are eroded more easily than the rock surrounding it, leading to the angular pattern. Then we look at radial. A radial pattern looks a lot like a hilltop, where water flows down the side, often reminds me of a volcano, where streams radiate outwards from a central point, normally a hill or a mountain, and they develop on a dome-shaped feature such as a volcano, hill, or mountain, where water is sourced from the top and flows down the sides of the land. Then we look at centripetal. Centripetal is the opposite of radial, where it flows inwards towards a point instead of outwards. The stream flows inwards towards a depression or a lake. The water does not flow out of the lake, it sits here. This is higher lying land than the lake, and therefore water flows down but cannot flow up. And these develop where there are central low-lying areas. Then we look at a deranged pattern, which is simply a haphazard pattern. There's no way to describe the pattern. Numerous lakes, swamps, oxbows, and meanders occur in this pattern, and they develop in areas which are geologically young. So there is no characteristic that causes the form of a deranged pattern, such as in the last patterns that we've seen, we can identify certain aspects that will lead to that pattern forming. The deranged pattern simply occurs in geologically young areas. Lastly, we look at a parallel pattern. These are rivers which flow parallel to each other. As we can see, the stream flows in the same direction down a slope. So we can see the tributaries join at a confluence and flow into the main river. And these types of patterns develop on uniformly resistant rock on slopes with a steep gradient. So much like the dendritic pattern, they form on uniform resistant rock. However, unlike the dendritic pattern, which forms on slightly lower gradients, the parallel pattern will form on a steep gradient where water flows very quickly, and we get this parallel pattern forming. Next, we take a look at drainage density. Now, drainage density is calculated using this formula here, where it's the total length of the streams in the basin in kilometers over the total area of the drainage basin in kilometers squared. Now, drainage density gives us an indication of how well a drainage basin discharges its water. A high drainage density gets water into channels quickly, and a low drainage density, more water flows over the surface and into the ground, gets the water into the channels more slowly. Factors that affect your drainage density: rainfall. Areas with high rainfall will have more water to discharge and thus a higher drainage density. That goes without saying, that if there's more water in a drainage basin, then there will be a higher drainage density as more water moves into the streams. Relief or gradient: steeper slopes have higher drainage density as they have more runoff and less infiltration. As we discussed when we looked at infiltration and runoff, a steep slope will lead to more runoff and therefore a higher drainage density. Permeability of rock and soil: permeable rock results in more infiltration and therefore lower drainage density. If you have impermeable rock, there is less infiltration and more runoff, and this would lead to a higher drainage density. When we look at the resistance of rocks, very resistant rock is not easily eroded. Therefore, few valleys are resulting in rivers being fewer numbers and a lower drainage density due to the fact that there are fewer rivers and therefore less water being moved into river channels. Vegetation cover also affects your drainage density. Vegetation slows down your runoff and causes more infiltration. Therefore, there is a lower drainage density in densely vegetated drainage basins. However, if you have less vegetation, your drainage density increases due to the fact that there is more runoff and therefore more water moving into river channels. When we look at drainage texture, a coarse texture has a low density with few rivers, as we can see in this diagram shown here, whereas medium texture has medium density of rivers, more rivers, and a fine texture has a high drainage density with a lot more rivers in your drainage basin. When we look at flood and drought conditions, a basin with normal flow would look something like this. Where we have flooding flow, we have many more first and second order streams, giving us a high drainage density. Our runoff increases and our flood peak on our hydrograph would be higher. In a drought flow, our first and second order streams dry up. As we can see, we have far less first and second order streams, and we have a low drainage density. Less water is moved into our river channels. Then we look at stream ordering. When we order streams, we start at the outside. We look at the outermost tributary on each river. So if we follow this river over here, our outermost tributary would be here. We would label it 1. This river over here would also be a 1 as it's the first tributary in its line. Where a 1 meets a 1, this river where after the confluence becomes a second order stream. In the same way, we have a first order here and a first order here, where they meet to the confluence. Following that, we have a second order stream. This stream over here would be a first order stream as there's nothing behind it or above it. And where a first order meets a second order stream at a confluence, the stream after the confluence retains the higher order stream. Therefore, it retains a second order stream. Over here, where we have a second order stream meeting a second order stream at a confluence, the stream after the confluence becomes a third order stream. And where a second order meets a third order at a confluence, it remains a third order stream. So when two streams of the same order meet, we add 1 to the order. As we can see, when a first and a first meet, it becomes a second. When two different streams of different orders meet, it retains the higher order. As we can see, when a second order stream meets a third order stream, it retains the third order stream. Then we simply put down our order, so 1, 2, 3, first order, second order, third order, and we calculate the total number of each type of stream that we have in our drainage basin. When we are asked to work out our bifurcation ratio indicated by RB is the number of streams over the number of the next order of streams. So if we look at first order of streams, then we would go first order over second order. So once again, we make a table of our orders, first order, second order, third order, fourth order, and the total number of each order in our drainage basin. In order to calculate our bifurcation ratio, we go first order over second order, so first order over second order, plus second order over third order, plus third order over fourth order, which we can see we've done here. So we take our first over our second, second over third, third over fourth. And we add them all together, we get 10.58, and then we must divide by the number of values that we've added together, in this case being 3, and we get an average of 3.53. Bifurcation ratio indicates whether an area is prone to flooding. It's a comparison between the number of stream branches of a given order to that of a higher order. So in this case, we can see that we have 3.53 streams. So if we say 3.53 first order streams flowing into second order streams, or a ratio of 3.53 second order streams flowing into third order streams. If that was lower, we would have 1 stream, first order stream flowing into a second order stream. If we had 1 stream flowing into another stream, we would have a lower chance of flooding than if we had 10 streams flowing into 1 stream. And in that way, bifurcation ratio indicates whether an area is prone to flooding. Then we move on to river flow. There are 2 types of river flow, laminar flow and turbulent flow. When we look at laminar flow, the riverbed is very level, as we can see in the diagram, and the velocity of the river is often low. The water will move in thin layers. The water flows in sheets, as we can see. There's no vertical movement of the water. When we look at turbulent flow, this is very different to our laminar flow. When the velocity of a river increases or the riverbed becomes uneven, as shown in the diagram, this will result in turbulent flow. The water forms eddies and bubbles, as we can see, and surface friction in the channel causes turbulent flow. There's now vertical movement of water. If you can picture a rapid or steep water that's flowing over a steep gradient and a very uneven surface, you can picture water that is not flowing smoothly down a slope, but rather with vertical movements and many eddies and bubbles. that is known as turbulent flow. In many cases, they will ask you to identify from a photo whether it is turbulent or laminar, and if you can see any bubbles or any indication that there's vertical movement of water, you can assume that it is turbulent flow. And when you have turbulent flow, it's good to note that your gradient is steeper and therefore erosion is likely to occur. Then we look at types of river loads. So our smallest type of river load is our solution load, which are minerals and dissolved substances in our water. Second smallest is our suspension load, which are fine insoluble particles which are carried in suspension in the water. Then we have a saltation load. Heavier particles bounce along the riverbed. So, as shown by the diagram, water moves the particles along and they bounce along the riverbed. They spend some time in the water and other times on the riverbed. And then we have bed load, which are the heaviest particles that are rolled along the riverbed and cause erosion as they do that. Then we look at types of erosion. Hydraulic action. The force of water on banks forces air into the cracks and bank weakens and falls away. When we look at fluvial landforms, we will see that this causes our meanders, it causes our oxbow lakes, and it plays a role in forming our waterfalls. Then we look at solution erosion, which soluble particles are dissolved in the water, and this results in chemical erosion. This can erode rocks and debris in the water, as well as the riverbanks. Abrasion, which occurs when rocks carried in the river wear down the riverbed and banks. So if you have a rock that bounces along the riverbed or rolls along the riverbed, the large rock particle erodes the smaller sand or clay particles of the riverbed, leading to erosion. When you look at attrition, this is when rocks in the river smash together and break down into smaller particles. So you can have two rocks moving along the riverbed. When they collide, they are broken down into smaller particles, and this is known as attrition. Then we look at our speed of flow. The energy of a river is determined by the gradient of the river channel, as well as the volume of water carried in the river channel. The gradient of the course determines the gravitational force. However, this is opposed by friction, both air, water, and the channel. So if you have a narrow channel, you will have a small volume with a great amount of friction, and therefore it will be slow moving. If you have a deep channel, you have a larger volume with decreased friction, as you have decreased area where your water is in contact with your banks, and therefore it's fast moving. And third case, you have a wide shallow channel with a small volume and great channel friction, and therefore the water is slow moving. When we look at discharge, as said, our energy is determined by our gradients of our channel and the volume of water in the channel. Discharge is equal to our width of our channel, times the depth of our channel, times the velocity of the water, times 0.8, which takes into account the friction experienced by the water. And we measure our discharge in cubic meters per second. When we refer to how full a bank is, these terms are good to know. If our river channel is underbank, this means that the water has not reached the banks of the river. If our river is bank full, it means that the water has reached the banks of our river, and any more water would cause flooding. And if our water is above the banks, we talk about it being overbank, which is when the river is in flooding flow. Then we look at something that is not particularly in the syllabus, but it is important to know and may help you. We look at wetted perimeter. Wetted perimeter indicates your frictional area. The greater the frictional area, the less energy the river has. So your wetted perimeter is indicated by the red in the diagram, and that is simply an indication of where your water is in contact with your banks and therefore your frictional area. We can use our wetted perimeter to calculate a hydraulic radius, which is a measure of the efficiency of a stream, and our hydraulic radius is calculated using our cross-sectional area over our wetted perimeter, which we use as a ratio, which simply tells us how much of our cross-sectional area is in contact with our frictional area, and therefore shows the efficiency of our stream.